Hello, this is alternating series estimation theorem. We are actually taking out part of the materials from 10.6 and 10.9 and putting them on this video. So we're going to start with alternating series estimation theorem, which was part of 10.6 when we talked about alternating series and alternating series test. So in the alternating series test, it says that if you have an alternating series like this and limit of Bn goes to 0, and if Bn is a decreasing sequence, then we can say that that's a converging alternating series, right? So here we're actually looking at something else. We are trying to understand what the remainder of an alternating series is. All right, so for example, we have this alternating series down here, -1 to the power of n-1 over n squared. Right. So let's say I take the first n terms, right, up to here. And then I just find the sum of the first n term, and I can call that S9, right? The partial sum of the first 9 terms. Okay. And whatever it's left, right, after that, after the first 9 terms, right, and the rest of them, we can call that the capital R over 9, which is the remainder of the first 9 terms. And the remainder of the first 9 terms, right? So these are the terms remaining if we take away the first 9 terms. And our goal in the alternating series estimation theorem is trying to understand how we can approximate the remainder, right? If you just take the first 9 terms, then what is the remainder, right? Can we find a limit for it? Is there a bound to it? And so on. Okay. And the whole thing, if we just add up the whole thing, right? The whole infinite sum, that's just S, right, for the sum. All right. So next, let's look at what the estimation theorem is. So the first part, the condition for the alternating series estimation is actually the same as the alternating series test, right? We have two things we want to check. Limit equals to 0 and Bn is decreasing. So this actually only works for a converging alternating series. And then it says then the absolute value of the remainder is going to be equal to the sum, subtracting the partial sum, right? S represents the total sum, and the Sn is the partial sum. And that is that less than or equal to Bn plus 1, which is the first term in the remaining terms. All right, so let's look at a quick example. All right, so let's say we stop at n equal to 7, right? So we're just adding the first 7 terms. So we can say that, okay, the total sum is equal to the partial sum of the first 7 terms plus the remainder of the 7 terms, right? So you can say that we're doing A1, A2, A3 plus plus A7 plus A8 plus A9 plus right? So the total sum means the whole thing. The whole thing is broken down into 2 parts, right? The first 7 term, which we're calling S7, and the rest of them, which we're calling R7. Okay. So this is basically what we're saying, right? The total sum is equal to the first 7 terms plus the rest of the terms. Right? And what we can do now is we're going to subtract S7 to the left hand side. So we have total sum minus partial sum of 7 terms is equal to the remainder of the 7th term, right? This is actually another way to represent the definition of the remainder. All right. And then when we take absolute value of R7, right, since it's an alternating series, we're not sure whether this is going to be positive or negative, right? So we're adding the absolute value is equal to the absolute value of S minus S7, right? Just like that, what we have here. And from the theorem, it's saying that this is less than or equal to B8 or A8. In this case, B8, yeah, right? So it's actually less than or equal to the first term in R7, right? So let's write it down. B8 is the first term in R7. Okay, so take a second to think about that, right? Just think about the terms. We don't have to understand well what we have here, actually. Is understand what's saying over here. The remainder of the 7th term, meaning adding B8 up to infinity, that is actually going to be less than or equal to B8, the first term in R7, because it's an alternating series, right? So the later term you look at is going to be smaller, which is not going to affect the first term that much. So the first term in R7 will actually have the largest absolute value, right? So everything after that, when we add it together, it's going to be less than or equal to that. All right, now let's try to understand this using a graphical approach. Let's say I stop here, right? This is 1, 2, 3, 4, 5, 6. This is B6. Right. So the first term in the remainder is going to be this value right here, right? That's going to be B7, right? First term after remainder. And this value, B7, is going to be greater than or equal to the rest of these values combined. You can see that after B7, the absolute value of the terms after B7 is going to be less than or equal to B7, right? And that's why in this case, B7 is the greatest term in the remainder series. So when we add them all together, since these are alternating, right, that's going to be bounded by B7. And the largest value, the largest remainder value can be is the value of B7. And depending on what sign B7 is, right, the remainder can be positive or negative. Okay, so this thing we're saying here is that the size of the error is at most the size of the first omitted term, right? That is what I was trying to show you using the graph and using this inequality up here. And that is also what the estimation theorem is saying, right? So the size of the error is at most the size of the first omitted term, meaning the first term in Rn in the remainder series. All right, and there are a few more things that we can say about this, is that the actual sum is actually between the partial sum minus the first term of Rn and the partial sum plus the first term of Rn, right? So we can actually show this pretty easily. Let's just take the example from earlier. S minus S7 is less than or equal to B8, all right? So we have S absolute value of S minus S7 is less than or equal to B8, right? And then this is just an absolute value inequality. We can solve this by dropping in the absolute value like that. Oops, S7 less than or equal to B8, right? And all we need to do is add S7 to both sides, right? So we have on the left hand side, we have S7 minus B8 is less than or equal to S is less than or equal to S plus S7 plus B8. Okay, so in the middle of the inequality here, we have S, which is the total sum, that has two bounds, right? The lower bound is S7, partial sum of the first 7 term minus the first term in the remaining series, or partial sum of the first 7 terms plus the first term in the remaining series. Right? So this is what another thing that we can say from the estimation theorem. All right. Now the last thing, the error has the same sign as the first omitted term, right? So the error that they're saying here is the remaining series, right? Rn. Right. So let's take a look. Right. Let's say, since we're looking at alternating series, right? So the terms are actually alternating signs. Let's say 8, 8 is negative, right? So notice that here we're using A instead of B, Bn. So the Bn that we used earlier, we are ignoring the alternating factor in the series, right? Assuming that B is positive. But here, since we're looking at including signs, we have to include the possible alternating factor in the series, right? So if A8 is negative, that means R7 is going to be negative, okay? Because R7 is the first term is AA, which AA is going to have the largest absolute value, meaning this is going to dominate the signs of the remaining series. And therefore, that means S minus S7 is less than 0, which means S is less than S7, right? S minus S7, that's just R7, right? Right. So S is less than S7. That means S7 overestimates. Right. So S7 is going to be greater than the actual sum, right? The partial sum of the first 7 terms. Right. So this is what we can say when we look at the sign of the first term in the remaining series. Now, on the other hand, if we get a 8, 8 is positive, right? That means the remainder is going to be positive, right? So we can say that, okay, the total sum minus the partial sum is going to be positive, right? Because the remaining series is positive. That means S is greater than S7, right? Total sum is greater than partial sum. That means, in this case, S7, the partial sum underestimates. Okay. Now that's a lot of information, right? So don't worry, we will take a look at an example and try to analyze these 3 items. All right, let's go back to this example we saw earlier. All right, so we have adding up the first 9 term, calling that a small S9, and then the remainder is going to be R9. Right? So what we can say here, from the alternating series estimation theorem, right, which is this thing, you can say that, okay, the absolute value of R7, R9, I mean, at the error, is equal to the absolute value of the total sum minus the partial sum, right? Which is going to be less than or equal to the first term in the remainder, which is 1 over 100. Now notice that since we're looking at the absolute value, we're taking also the Bn part of the series, so meaning the absolute value of that as well. So it's going to be less than or equal to 1 over 100. Now from this, we can say that, okay, then that means negative 100 is going to be less than or equal to S minus S9, less than or equal to 1 over 100, right? By solving the absolute value inequality. And then when we solve this, we get that S9 minus 1 over 100 is going to be less than or equal to S, less than or equal to S9 plus 1 over 100. Right, so the actual sum, right, this is the actual sum, is going to be between these 2 things, right? So let me write that in terms of the notation, right? Sn minus bn plus 1 and Sn plus bn plus 1. Okay. So this is what we saw earlier, just putting that in context of this problem. And that's identifying the sign of the first term, right? So the sign of error is going to be equal to, it's going to be the same as the sign of the first omitted terms. Right, so the sign of the first omitted term, which is this circle 1 right here, 1 over 100, which is negative, right? So that means R9 is going to be negative, right? Let's write it down. All right, so the sign of the first omitted term, it's going to be A10, which is negative, right? Negative 1 over 100. All right, so R9 is equal to S minus S9, which is negative, right? Since A10 is negative 100. That means S9 is greater than S, right? The partial sum is going to be greater than the actual sum. That means S9 is an overestimate. Okay, so pretty easy, right? You just need to look for how many terms you want to look at, and then use the first term in the remaining series to build an interval where your actual sum is going to be in. And then by looking at the sign of the first omitted term, we can understand whether the partial sum is going to be an overestimate or an underestimate. All right, now let's look at an example where we have ln of 1 minus x, and then the power series is given to us. So let's see. Starting by writing out some of the terms, right? So ln of 11 over 10, we can write this as ln of 1 minus negative 1 over 10, right? That way it's in the form of ln of 1 minus x. And let's write out what we have, right? So if negative 1 over 10 minus what is that? Negative 1 over 10, 1 over 100 over 2 minus 1 over 1000 over 3, and so on. Oh, negative 1 over 1000. All right, so that will be 1 over 10 minus 1 over 200 plus 1 over 3000, and so on. Okay, so S2 is just these two values, right? That's S2. And then the remaining of them, it's going to be R2. All right, so S2 is 1 over 10 minus 1 over 200, right? So that comes out to be, it's 95 over 1000. Yep. Oops, no, actually, we need to do that. That's 19 over 200. Okay. And then we know that S, absolute value of S minus S2, it is going to be less than or equal to R2. Right. But we don't actually need to worry about that, but we can actually write it out. So that becomes S minus 19 over 200. It's going to be less than or equal to, sorry, not R2, B3. Right, so the first term in the omitted series, 1 over 3000, right? And then we know solving the inequality, we get that this is actually 19 over 200 minus 1 over 3,000. That's not equal to 19 over 200 plus 1 over 3,000. Right, so the actual sum is actually between these two numbers. And let's see what these two values are. All right, so the actual sum from the inequality is actually 142 over 1,500 and 143 over 1,500. So it's very close, right? We can actually bound that to be between the range of 1 over 1,500. And of course, the more terms you use, the better your approximation is going to be. All right, now we want to see whether this is an overestimate or underestimate, right? So R2, oh, not R2. Um, the first omitting term, A3, is positive, right? That means R2 is positive, right? R2 greater than 0, meaning S minus S2 is also positive, right? S is greater than S2, right? So S2 is smaller than S. That means S2 is an underestimate. Okay, there you go. Now in 10.9, when we look at Taylor's series, we also have the Taylor estimation theorem. Right, so it's basically walks you through a similar idea using Taylor's formula and Taylor series theorem. And we have this Taylor estimation theorem or a remainder estimation theorem. Now this is actually optional for this class, so I'm just gonna show you guys in a few what the theorem actually says, and if we have time at the end of the semester, we will cover this as well. But for now, this is just something to look at. But what I really want you guys to focus on is the first thing, alternating series estimation theorem. And this is the stuff that you actually need to know. For the Taylor estimation theorem, we don't have to worry so much about that. And that's it for today. Thank you guys very much.